It's a classic whodunit, a tale of intrigue and hidden motives, except the crime isn't confined to a mansion or a dark alley, it's happening inside your own body, within the intricate network of your being. The victim, the central nervous system, the command center that controls everything from your thoughts to your movements. It's under attack, not by an external force, but by its own immune system, a case of mistaken identity with devastating consequences. This internal conflict is known as multiple sclerosis, or MS, a condition that affects millions worldwide. Imagine your nerves as electrical wires, the pathways through which signals travel throughout your body. These wires are protected by myelin, a fatty insulation that ensures signals travel quickly and efficiently. In MS, that crucial insulation is stripped away, leaving the nerves vulnerable and exposed. This damage scrambles the signals between your brain and body, disrupting communication and causing a cascade of problems. The result? A wide range of unpredictable symptoms that can vary greatly from person to person. It could be blurry vision, making it difficult to see clearly, or a persistent tingling sensation like pins and needles in your hands and feet. Profound fatigue and overwhelming exhaustion that doesn't go away with rest is another common symptom, and trouble with balance, making it difficult to walk steadily or maintain coordination. The frustrating reality of MS is that no two cases are exactly alike. The symptoms and their severity can differ significantly. These attacks on the myelin leave behind lesions, areas of damage in the brain and spinal cord. These lesions are visible as bright spots on MRI scans, providing valuable clues for diagnosis. MS often strikes in relapses, periods of intense symptoms, then retreats into periods of remission. But over time, the damage can accumulate, becoming permanent and leading to progressive disability. For years, scientists searched tirelessly for the mastermind, the underlying cause that triggers this devastating autoimmune response. They sought to understand what was behind this internal sabotage, this betrayal by the body's own defenses. Was it genetics, a predisposition passed down through generations? Or was it the environment, exposure to certain toxins or infections? Or perhaps a complex interplay of both, along with other unknown factors? The immune system was clearly the weapon, the instrument of destruction in this internal battle. But the true trigger, the initial spark that ignited this autoimmune firestorm, remained a frustrating mystery. The investigation was incredibly complex, a puzzle with countless pieces, but the search for answers, for effective treatments, and ultimately a cure never stopped. In MS, the body's own immune cells, T cells and B cells, turn traitor. T cells, the frontline soldiers, cross the blood-brain barrier and attack myelin, unleashing inflammation and damage. B cells, the intelligence agents, produce antibodies that mistakenly target myelin as well. It's friendly fire on a devastating scale, with both T cells and B cells fueling the assault. For years, T cells took the blame, but a breakthrough came when B cell targeting treatments dramatically reduced MS relapses. Suddenly, B cells were in the spotlight, no longer just accomplices, but possible masterminds. The question shifted: what convinced these immune cells to turn against the body? Scientists realized they weren't just dealing with rogue agents, but with a deeper mole in the system. The hunt for the true instigator intensified. The next big clue was about to emerge. Enter the Epstein-Barr virus, or EBV, a microscopic entity with an outsized impact on human health. It's the common culprit behind mononucleosis, often referred to as the kissing disease, known for its fatigue and discomfort. Nearly everyone gets EBV at some point in their lives, often during childhood or adolescence, but for most individuals the infection is harmless, or produces only mild symptoms, and the virus goes dormant in B cells for life, quietly residing within the body's immune cells. The twist? Almost every person diagnosed with multiple sclerosis, or MS, has had an EBV infection sometime in their past. The connection is undeniable. A massive long-term study revealed that the risk of developing MS skyrockets dramatically after an individual experiences an EBV infection, a truly significant increase. For many researchers, this discovery was the smoking gun, the critical piece of evidence linking EBV to the development of MS. But if EBV is so widespread, infecting the vast majority of the global population, why is it that only a relatively small fraction of those infected go on to develop MS? What other factors are at play? The answer, or at least a significant part of it, lies in a complex interplay of genetic susceptibility, meaning some individuals are genetically predisposed to developing MS after an EBV infection, and also a particularly cruel case of mistaken identity within the immune system. EBV's protein, known as EBNA1, bears a striking resemblance to a protein found within our own nervous system. This mimicry is key. When the immune system launches an attack against EBV, targeting the EBNA1 protein, it can sometimes mistakenly identify and attack our own cells, specifically those in the nervous system, due to the similarity in protein structure. The devastating result: a tragic case of friendly fire where the body's own defenses turn against itself, causing damage to the nervous system. All triggered by EBV, a master of disguise that cleverly mimics our own proteins. EBV doesn't act alone in the development of MS, it's part of a complex web of factors. But in individuals with the right genetic predisposition, EBV is often the spark that lights the fuse, setting off the chain reaction that leads to MS. The intricate mystery of MS was finally coming into sharper focus, revealing the crucial role played by this common virus. The case isn't closed, and the investigation needs you. MS research is moving fast, and staying informed is your way to join the team. Subscribe for updates on new suspects, breakthroughs, and potential cures. We break down the science so you can follow the case, no PhD required. Liking and sharing helps spread the word and fuels the search for answers. The more people involved, the closer we get to solving MS. Join our community of curious minds and stay on the front lines of discovery. The next big break could be just around the corner. If EBV is so closely linked to multiple sclerosis and is believed to be a key trigger, why not just develop a vaccine? Why not create a preventative measure and stop MS before it even has a chance to start? It seems like a logical solution, doesn't it? Unfortunately, it's not that simple. The development of an effective EBV vaccine faces some significant hurdles. EBV is a master of disguise, a shapeshifter in the microscopic world. It has the ability to hide inside B cells, those crucial white blood cells where it can remain dormant for life, evading detection by the immune system. Vaccines usually work by training the immune system to recognize and spot invaders, preparing it for future attacks. But EBV's ability to go dormant, to essentially become invisible, makes it a moving target, a constantly shifting challenge for vaccine developers. The virus has multiple life stages, transitioning between active replication and dormancy, and it changes its appearance during these stages, making it incredibly hard to catch and neutralize with a single vaccine approach. Despite these challenges, scientists around the world are actively developing vaccines to block initial EBV infection. Other strategies focus on training the immune system to specifically hunt down and eliminate those B cells already infected with EBV. Some of these experimental vaccines use mRNA technology, a platform that gained prominence with the rapid development of the COVID-19 vaccines. These promising EBV vaccine candidates are now undergoing rigorous testing in clinical trials. If successful, a vaccine could prevent future cases of EBV infection and potentially reduce the risk of developing MS in susceptible individuals. However, it's important to remember that a preventative vaccine won't cure those already living with MS. For them, the damage to the nervous system is already done. Therefore, the investigation into MS and its causes must continue on other fronts, exploring potential treatments and therapies. Developing a way of stopping EBV is undoubtedly a huge step forward in our understanding of MS, but it's not the whole answer to this complex and debilitating disease. What about those already affected by MS? There's hope. Disease-modifying therapies now slow the disease and reduce relapses, giving people better lives. The next frontier: repair and regeneration, stimulating the body to rebuild myelin and fix the damage. Stem cell therapies and drugs to awaken the brain's repair mechanisms are in development. The EBV-MS link has opened new avenues, including antiviral drugs to target the virus in B cells. We're moving from managing symptoms to targeting the root cause. The case isn't closed, but for the first time, the clues are pointing toward a solution. The final chapter is still unwritten, but hope is on the horizon.